mind. Now we'll go. Okay. So we're I did send out an email. There's no quiz today because I was thinking about it, and it's like, well, I have one day to cover material, and there's no shot I can cover everything I would want to make anything that isn't just like some boring like throwaway. Here's homework for the sake of homework type of deal. So I was like, I'm not doing that. Like, I'll just skip one. Who cares? Because well, normally because it's Wednesday, right? So normally we would do one on Wednesday, but we didn't have class on Monday. So it's like, okay, well, I can't. There's no shot I'm covering enough stuff in one day. With recursion, it worked out great because that's a short enough topic that I could cover it. But this is like, okay, we're jumping into like a brand new chapter that's going to last the rest of the term. So no, we're not. we're gonna. I'm gonna cover what I can cover, and then we'll finish it next week, and then I'll move on to the next topic next week, which means, yeah, there might be like one extra question on the quiz next week, or I'll take one out and then replace it with something else. But yeah, there's just the one. Yeah, I normally hand it out on Wednesdays. Yeah, so then I can make it due on Saturday. Well, I mean, there's only gonna be like 2 more, so it's like whatever. We're gonna start with some extremely exciting sounding math. If I could spell, which I can't. So we're talking about geometry and algebra of vectors. So, vectors are something that maybe you've heard of before if you took physics. It is that same exact concept, but we're going to go a bit more in depth. So why would we care about this topic, specifically linear algebra? Well, there's a lot of reasons why programmers should care about linear algebra. One of them is it teaches very specific problem solving and abstraction thinking skills, which is very important for you're working at a company and they say solve this business problem, which is very abstract, and you need to make it concrete. Well, good thing you learned linear algebra to think that way. But primarily we're going to be talking about vectors and then matrices, which are, well, you can represent a vector as just an array, and you can represent a matrix as a two-dimensional vector, or two-dimensional array. So you'd have just 2 indices for indexing your array, and that's a matrix, right? So linear algebra is a convenient excuse to get you working with those sorts of objects in a programming sense. So that's great. Vectors, the geometry side, useful if you have any passing interest in graphics or game design, right? It's just, you need to know how vectors stick out of things and how they rotate, and they're useful for physics calculations. So I would say that's the elevator pitch of why do we care about this topic? Why are we talking about it? And honestly, the main topic is the Marge meme. I just think they're neat. It's something I love talking about. It's useful to you. So we're going to talk about it. So we're going to start with sort of just all of our definitions. We're going to start by talking about vectors in R2. And we're sort of going to follow a similar motivating pattern that we've had for a lot of the other topics, like when we talked about set theory, we talked about the words symbolic logic, that sort of thing, where we're like, okay, we've defined this concept, now what can we do with it? But the interesting thing about vectors and linear algebra is there's the algebra side of things that we're always talking about, but there is an underlying geometry too, all the time, which is why it's interesting, right? There's always that connection. Whatever we do in algebra, there is some corresponding geometric idea behind it. So the first thing we're going to do is just define a vector. So a vector is a directed line segment from one point to another. So one thing that's going to be kind of the struggle with this topic is there's a lot of geometric concepts. Trying to write a geometric concept in words is hard. So I'm going to write down the definition, and you're like, sure, whatever. And then we'll draw a picture, and you'll be like, okay, that the picture is what we should take away from it. So we've got our standard XY plane, right? Just as normal. That's what we're going to be looking at right now. And what this is essentially saying is we're going to go from one point, which we'll frequently call, say, A, and we're just going to go to another point. Let's call it B. Now, it says it's a line segment, but it's directed. So what that really means is, yeah, it's a normal line segment. It's a line connecting the points A and B. But now we care about a direction, right? We're going from A to B, rather than it just being something connecting A and B, right? Where we could go either way. No, this vector is going from A to B. So there's a couple of notations for this. Notation. So one of the ones, especially if we know the 2 points like this, would be this. It's basically saying, I mean, we've got this arrow indicating from A to B. That's really what this notation is saying, right? It's the line that the arrow is pointing, go from A to B, right? Pretty intuitive. The one that we use the most, though, is just a letter, a lowercase. My V's look like U's today. A lowercase letter with a line above it or an arrow above it, just like this, that indicates vector. In print, especially in my notes sometimes, you might see this, which is hard to write on a whiteboard, so we won't use that at all. It's just a bold-faced letter. Will often indicate a vector as well. So if you're just looking at, books or things on Wikipedia or whatever, all three of these notations mean the same thing. So we have this concept of essentially a starting point or initial point, right? That's where we start from, and then we point to an end point or terminal point. Terminal and initial are what I would say more mathy ways of saying it, but I tend to stick to end and start because those are just, you intuitively understand what those mean. It's just the end point and the start point of our vector. Okay, so that's the basic concept of vectors, but we need some way to like write down different vectors, right? We're not just gonna, you can't represent this in a computer very easily, right? We need some way of representing it otherwise. So recall that R2 is all the ordered pairs A comma B, where A and B are real numbers. Right? They're points. They're the points in R2, right? That's what this means. So a vector let's call it V in R2 looks like the following. It's almost the same thing. It's an ordered pair of numbers, but now we're using square brackets. So, you might say, well, Travis, if you just change the brackets, that doesn't change what it is. Well, that's why we use different brackets for it, because they mean and represent completely different things. In fact, this R2 and this R2 are technically, in a way, different things, because we're saying this R2 is the collection of points. This R2 is a collection of vectors. It doesn't really matter. Just make sure that you are distinguishing between them, right? If it's a point, that's round brackets. If it's a vector, that's square brackets. So this is called a row vector. But it's also common to represent it as a column. Where just these are numbers, right? V1 and V2 are numbers. They're real numbers. Okay, so I'm saying that these represent something different than just our standard points. So what does it represent? Well, we go back to this. A vector is a directed line segment. So that means there's a direction involved. And also there's some kind of notion of length here. So the components v1 and v2 mean something. They represent displacement. So essentially movement. So for v1, that's horizontal. So along the x-axis, right, left and right, v2 is vertical. So that's along the y-axis. Now, if v1 is bigger than 0, what we're going to do is we're going to move to the right. If v1 is less than 0, we move left. And if v1 is 0, we don't move. And the same idea for v2, right? If v2 is bigger than 0, we move up. If v2 is less than 0, we move down. And if v2 is 0, no move. So that's the difference, right? Here, well, in a sense, this kind of represents that 2 in a different way. You know, if we wanted to draw the point 2, 1, we would move right 2 and then up 1 and just draw a dot there, right? We would say, there's the dot that represents this point. Whereas with vectors, we're actually drawing a line segment, right? From somewhere to somewhere else. Okay, so now we have this idea of vectors. When are they equal, right? What does it mean for 2 vectors to be the same thing? When are 2 vectors equal? Well, in an abstract sense, they represent the same displacement, right? You move in the same exact way, the same distance. So 2 vectors are equal if they have the same length and direction. So same displacement. So something to note here is that the definition of vectors being equal does not say anything about where the vector starts, right? Just that you move in the same direction the same amount. So that actually is an important distinction with vectors. We can actually start them wherever we want. And that kind of makes sense when we think about what these components mean, right? This just tells us how much we move left or right. This just tells us how much we move up and down. It tells us no information about where we start, right? We can start anywhere. We just move 2 and up 1. No matter where we started, that's what a vector represents, right? It's a displacement of 2 along the x-axis and then up 1 along the y-axis. So algebraically, though, this is exactly what you would hope it to be. So u equals v as vectors if, so this vector here is going to be u1, u2. This vector here is going to be v1, v2. So they just look like that. We're going to say they're equal if u1 equals v1 and u2 equals v2, right? Exactly what you would expect. Just they're equal, the components are the same thing. And this makes sense, again, because if this is how much we're moving to the right, well, they need to move the same amount to the right. and they need to move the same amount up or down, right? Okay, but because these vectors sort of have, we don't care where we start them, there is a specific point where we like to start them often. So a vector is in what's called standard position. If it starts in the place that you would think is natural to start a vector, the origin. If it starts at the origin. So I would say it's pretty common that we'll draw vectors from that position if it doesn't matter where we draw it from, but sometimes it's convenient to draw it from somewhere else, and then we'll draw it from there. So let's just do an example. So the following vector, 2, -3. So we're going to draw this thing. Okay. So again, it does not matter where we start. So I could start, say, let's start, I don't know, here. Right, so what does this vector tell us to do? Move right 2, down 3. Wow, that's terrible straight line, I can't. There we go. So we moved right 2 and down 3. That's what this vector represented. But like I said, we often want to start in standard position just because it's nice to start at the origin. It's nice to have a common starting position, right? So we just try to start everything from there if we can. So it says start here, go right 2, down 3. Right? And if my axes aren't completely awful, these vectors look basically the same, just shifted, right? We just took this and sort of moved it over here, right? But this one is in standard position. So we'll remark on that. These vectors look the same. They look the same, just shifted. And that's kind of the key point for equality, right? They're the same lines and arrows, just moved around a bit. And that's how you know they would be equal. So if we were to draw, say, let's do -1, 2. So this vector, from the same position, we move left 1 and up 2. We see that obviously these aren't the same thing, right? They don't have the same direction. They don't move the same amount. They look completely different. And moving this around is not going to change that. So now, let's draw another vector. Two minus 1. So this vector goes right 2 and down 1. Which again, also looks completely different from them. Now, notice here that V and W just have their components swapped, right? -1, 2 versus 2 minus 1. So this was true for points, right? We said they're ordered pairs. Also true for vectors. We can't just swap the order of them, right? We have to, the order of the components matters. And this especially makes sense here, right? That first number tells us how far we move along the x-axis, and the second number tells us how far we move along the y-axis, so swapping them around isn't going to give the same result. So the order of components in vectors matters. So don't just swap them around willy-nilly, right? They're in the same order all the time, right? You have to pay attention to the order that you write them in. Okay, but this concept of equality lets me sort of draw attention to what will become a very important concept in linear algebra in our discussions of it. So find x and y, which are real numbers, such that the following is true. 3x comma x minus y is equal to 6 comma minus 2. Okay, so, yep.
Sorry, I have to take you back.
Hmm?
This line.
Which one?
The first one. No. Yes.
This one?
No, down. Yeah, how did you draw that one?
So I just picked a random starting point,
Okay.
and we move right 2 and down 3. Which is what this says for displacement, right? Move right 2 and down 3 from where we started.
Yes, for that one, I see that you came here. Sorry, class, I have to go to the bus.
That's totally fine.
You see that this one here, you came 1, 2, right?
Mhm.
And then 1, 2, 3.
Yep.
And then you did the points and then you drew it.
Yep.
Right?
Yep.
For this one.
Yep.
So this one, how did you do it?
It's the same thing. That's the exact same one, right? I just started here,
Okay.
move right 1, 2,
Okay.
and then move down 1, 2, 3.
Oh.
So the point here is that you can start drawing a vector from wherever you want. It doesn't matter, right? They're all this. So this vector drawn this way and this one, they're the same vector. We just drew them somewhere else, right? So that is an important distinction. These are the same thing, just shifted, right? And if I said draw this vector and you drew this, you'd be correct. Or if you drew this, you would also be correct, right? Both of those are fine. Okay, so we're trying to find x and y so that this equation is true, right? That these two vectors are equal to each other. Now, if these two vectors are equal to each other, it just means that, the first components are the same and the second components are the same. This means that 3x is equal to 6 and x minus y is equal to minus 2. Now, this seems like kind of a weird, specific, silly example, but the reason why I'm doing it is this right here is called a system of linear equations. And that is like the building block of linear algebra. This is the thing that we care about the most. We're going to get there. We're talking about these vectors first, and then we'll talk about connections between these things. But solving these two equations simultaneously is very, very important to linear algebra. And it's something that is covered in high school, but like briefly. And the techniques that I would expect you to solve this are exactly what we're going to use right now. We're not going to do anything fancy. We're going to say, okay, well, we've got these two equations. They both have to be true at the same time. So this first equation here, 3x equals 6, tells us that x has to be 2, right? We just divide that first equation by 3. We get that x has to be 2. So now that we know that x has to be 2, we've got the second equation. And well, now we know what x is. Right, so we just plug it into every other equation, right? So x is 2. This bottom equation becomes 2 minus y is equal to minus 2, and now we just have to solve for y, right? We just move stuff around and isolate y. So 2 minus y is equal to minus 2. That will become minus y is equal to minus 4. So y is equal to 4. So that means this vector equals this vector when x is equal to 2 and y is equal to 4. And we can check that, right? If we plug in x is 2, we get 3 times 2, which is 6. Okay, good. The first two things are the same. Now we plug in x is 2, y is 4. So 2 minus 4 is minus 2. Good. Those are the same things, right? So these two choices of x and y make these two things the same. Now, the reason why I'm doing this is just to sort of give you a brief reminder on this technique for solving equations. We're going to spend a lot more time on that. We're going to go back to it, but this is just a sort of a taste of it, right? And mostly pointing out that, the fact that vectors are equal to each other lets us do this sort of thing. Okay. Now, I want to mention here, this is another remark, and it kind of makes sense from here with the fact that vectors we can move around however we see fit. Don't get vectors and points confused. So vectors and points are different things. Right? Points are just a single dot in space. Vectors represent direction, right? They're this line segment, right? So they're not the same thing. But there is a way to get a connection between them. So there are connections, though. So we can get a vector connecting two points. Connecting two points as a formula. And unfortunately, that formula has a nice mnemonic that I just remembered. It's terminal minus initial. Or end minus start, however you want to think about it. But let's just see it with an example. So let's take 2 points. A is, do I have them written down so that I can actually yeah. 0 minus 1 is a point, and B is 2, 1. I had to look at my notes because I just invented numbers for my previous class, and the numbers ended up really bad, and I couldn't draw it very well. So I was like, okay, I'm going to use the numbers that I already cooked up. Okay, so what this looks like is we've got our points. So this is 0 minus 1. So this is our point A. And we've got this point B, 2, 1. Like that. Those are our 2 points in space. Okay, so what I'm saying is the formula for this is terminal minus initial. So the vector connecting A to B. So when I say terminal, I mean the end point. So that's this. And when I say minus, I mean the natural thing, right? Actually minus. So 0 and minus 1. Right? We just take component-wise the end point and subtract off the starting point. So what does this give us? 2, 2. So this is saying move right 2 from A and up 2, and you'll reach B. So let's actually just draw, without even looking at this, that's the vector connecting these 2 points, right? Naturally, right? Just looking geometrically. Does this match what we just found? So we go right 1, 2, and then we go up 1, 2. That's exactly what we just found, right? So this definition here, this formula for doing this, actually accurately represents the vector that connects these 2 points, right? You go from here to here in terms of displacement. And this is just a formula way of finding out how much we move to the right or left and how much we move up or down. Okay, but this just tells us how to connect 2 points. So there is actually a natural connection between points and vectors. So if we let our initial point be the origin, well, what happens here, right? So we would go from OB, and in terms of, this point B, we're gonna say B is now some abstract point, right? Not numbers anymore. It's just a random point. Put whatever numbers you like in there. So it's going to be B1, so terminal endpoint minus the initial point, end point minus the initial point, gives us B1 comma B2. This is the same thing, just square brackets versus round brackets, right? But what this is really meaning is, let's say B is 2 comma 1. Yeah, we'll use the same point. So this is our point. Now we're saying OB is just 2 minus 0, 1 minus 0. We go right 2, up 1. So now we're just going from the origin to that point. So now there's a correspondence between points and vectors, right? If we just take the point and plug it into the vector notation, it just tells us how to essentially walk to that point. So vectors from the origin point, or I don't want to use point in the same sentence. Point to the point sounds very weird. Indicate the path to a point. Right, we've just got this natural connection, right? Vectors and points, they connect to each other. So, okay, there are a couple of important vectors that we care about pretty frequently. Oops. So, important vectors. So the first one is the zero vector. So it makes sense. We're calling it the zero vector. It has nothing in it. So, okay. This obviously has length 0. Right? It doesn't go anywhere, right? And no meaningful direction, right? Because you don't go anywhere, so what direction did you go? Well, that's not even something that really makes sense to ask, right? You didn't go anywhere, so you didn't go a direction. But that also means we can intuit that we can kind of give it whatever direction we want. So like, just imagine, I'm standing here. I walked that direction, but I didn't go anywhere, right? Or I went this direction. No, I didn't move, but that's the direction I went. So in a sense, the zero vector has no direction and whatever direction you want, right? Because you just face somewhere and don't go anywhere, and you could face a lot of different directions. So the reason why I'm mentioning that is sometimes it's just convenient to say, yeah, the zero vector pointed a specific way, right? Even though it doesn't really point anywhere, it just might be convenient to give it a direction if we need it. There's also the standard unit vectors. So these, you'll see why we care about them. So they're pretty simple. The first one is just put a 1 in the first component. The second one is put a 1 in the second component. So what do these actually represent? Well, this first vector, E1, starts at the origin and points that way. So it goes along the x-axis, right? What about this one? Goes along the y-axis, but just 1 unit up. So things of length 1 are important in mathematics. They're just really convenient. They work out really nicely. An example that you would know about is the number 2 pi is the circumference of a circle of radius 1. We care about radius 1, right? It comes up a lot. So same thing here, length 1, right? We move exactly 1 unit up or exactly 1 unit right. These end up being important, right? We just care about moving one unit because it's controlled, right? So we gave these a special name because they just represent the axes. And you can kind of think that, you know, if we just did a bunch of these vectors to the right, they're sort of capturing every other vector, right? Just put a bunch of these in a row, like 5 of them, and then you walk along it and you went 5 to the right, and then you put a bunch of them in a row here and you went up that amount. So they sort of capture all the other vectors in a way. Okay, so just like with all the other times we've talked about this when we did, you know, symbolic logic and set theory, now we have a new thing. We have a new toy to play with. So let's start playing with it, right? Let's find some things that we can do to this object. So when we're thinking about, you know, a math thing, and we just talked about a way to make them equal to each other, what's the next natural thing that we want to be able to do when we're dealing with numbers? Just guess. So we've got equal. So what are things that we can do to numbers? Yeah, right. We can add numbers. So can we add vectors? It's a natural question. Or, I mean, maybe not. I mean, the fact that I'm phrasing it that way means like, yeah, we probably could. Otherwise, I'm just like pulling your leg for no reason. So we can do operations on these vectors. And naturally, the first one is addition. So for vectors, u and v in R2, their sum, u plus v, or is, it's not noted, that's the notation. It's exactly how you would expect. We just do it component-wise, right? We've got some vector u and some vector v, and they have components. And we just add them up in the natural way, right? So component-wise, and actually I'm gonna specify up here, u is the vector u1, u2, and v is the vector v1, v2, just in case you want to write that down for reference. So just as an aside here, you're probably starting to notice it. The notation in linear algebra is just kind of like that. You eventually get used to it. You have a lot of subscripts and indices and that sort of thing. And the reason why I say you will get used to it is because what's something else that has a bunch of indices and indices inside of indices and looping and subscripts and stuff like that? And it's programming, right? You do for loops inside of for loops. That's just indexing inside of indexing, right? So this sort of ugly notation ends up being something that you run into a lot in programming. Maybe not specifically linear algebra, but the concepts of thinking like this matches looping, right? There's a lot of overlap here between for loops. So the notation gets a lot. It can be a lot to unpack. So it's important when thinking about linear algebra concepts to ask yourself, how do I distill this, right? What's really going on here? So especially when we talk about some of the operations we do on our vectors in Rn, so that means there's an arbitrary number of components. It looks really ugly. So when we distill it, though, we're just like, oh, we're just adding component-wise, right? Just, you know, the first one, mash them together. The second one, add them up. The third one, add them up, and so on, right? That's the key takeaway here, is we just do it component-wise. So the notation might look really ugly, but the concepts of what we're doing are not that complicated, right? It's just the notation that looks really bad. So just as a quick example here, so let's let u be the vector 2, 1, minus 1, 3. So column vectors and row vectors, we can write vectors either way. I would recommend sticking to one notation though in an individual problem. So like it's technically fine to write a column vector here and a row vector there, but it's a bit weird. So I would just say just be consistent. It doesn't matter which one you do. Pick one. Like if you want to write it as like this, that's fine. If you want to write it like this vertically, also fine. But just pick one. So the point here is u plus v. What is it? Well, we've got 2, 1 plus minus 1, 3. So component-wise, we just add the components up, right? So 2 plus -1 and 1 plus 3. That's it. Just add them component-wise. So 2 plus -1 is 1. 1 plus 3 is 4. And we're done. So again, the notation, I mean, this isn't too bad, but like there's just a lot of symbols, right? There's, you know, V1s and V2s and U1s and U2s. But the point is component-wise. Now, in our previous discussions, like with set theory and in symbolic logic, this is where we would stop. We would be like, all right, on to the next one, right? Let's talk about a new operation. But vectors and linear algebra is unique because we have some geometry going on, right? These all represent a geometric object. So we can visualize addition. So there's two ways to do it. One of them is called the head to tail rule. And I'm going to write this in words, which I apologize for because writing it in words is pretty awful initially. But then when you see the actual visualization of it, you're like, okay, that's fine. Right? It's the words that are bad. So position, this pen is not better. So position B, so that its initial point coincides with the end point of U, or terminal point of U, then the sum is the vector connecting the initial point of U point of U to the endpoint of V. And now you see what I mean. That's writing that in words is a lot. So let's unpack it so that we can actually see the geometry going on here. So what this is saying is, okay, we've got some vector U like this, right? Now, we're going to take V so that its initial point, so the starting point, coincides with the end point of the vector we just drew, right? So we've got the starting point of the new vector is the end point of the previous one. We're going to draw it like that. Now, the sum, U plus V, is just take the initial point of our first vector and connect it to the end point of the other one. So we just get this triangle. That's all it's saying, right? It's in words, it's saying a lot, but we just have this motion, right? To add them up, we draw U, and then from where we just ended, we draw V, and then we complete the triangle. And that gives us U plus V, right? So the words are worse than the picture. So now, there's another way though, and that's the parallelogram law. This pen is actually worse. So the big difference here is that we just start our problem differently, right? We're just going to start drawing it differently. So position U and V to have the same starting point. So something like this. I'm going to try and draw the same vectors. So this looks a bit like that. That's our U. And then we've got our V, which looks a bit like this. All right, so we have the same starting point. So now what we're going to do, well, it's called the parallelogram law. We just create a parallelogram. So finish the parallelogram. So if you don't remember what a parallelogram is, it's a rectangle that's maybe rotated, right? Just this board is a parallelogram. If we just rotate it, it's still a parallelogram, right? So what I mean by finish it is just we're going to create little dots and we're going to make our rectangle. Right? We're making that parallelogram. Now, U plus V is the diagonal from that same starting point. So what I mean is this is our starting point for both the vectors. We start at the same spot, go along the diagonal. Right, and we get U plus V. So these look like the same vector, right? We drew it in a different way, but these rules actually are inside of each other, right? If we just cover up the top there, right there, we've got that rule over there, right? Same thing. So it's just down to how you visualize it, right? This would also be V, because again, we can draw a vector from whatever point we want, right? Does not matter, as long as it follows the same displacement. So which one should you use? Up to you. If you have to visualize vector addition, whichever one makes more sense to you. For most people, this one usually clicks because, I mean, you draw a vector, and then from where you just ended your pen, you draw the other one. So like it's kind of natural to just sort of connect the dots like that. This one is a bit more abstract, and it's easier to not mess up, make inaccurate, because you have to do this like dotted part of the parallelogram. So it can be a little messier. But if this works for your head, then I will never specify which one you need to do. Just pick one. And our focus is not like, I'll have you do like one drawing of vectors and then I'll be like, okay, that's good enough. Just so that you get the visualization. So let's just do an example of drawing. So let U be the vector 2, 1. Again, I'm using the same numbers here so I don't get something that is flying off the board. 1, -1. Okay, so let's actually just start by drawing the picture, right? Because my point here is that it's geometric. So we should start with that. So let's do the head to tail rule. So first, we're going to draw our vector U, and what it says is go right 2, up 1. So we're going to go right 2, up 1. Right there, that's our vector U. Right? Now, all this rule is saying is from where we just ended, do the next vector, right? We go right 1 and down 1, and that gives us V. So then what's U plus V? It's just the end point of the first one, or sorry, the start point of the first one to the end point of the second one, u plus v. So this vector how much did we move to the left or right? So 1, 2, 3 to the right. And yeah, we didn't move up or down, so this is a 0. So just from our geometry, this is what we expect the vector to be, right? Now let's actually do the algebra. So u plus v is 2 plus 1, 1, 1 plus minus 1, so 3, 0, right? So we did this geometry picture independent of this algebra, and we got the same result, right? So this geometry is always behind the scenes, which is what, to me, makes linear algebra interesting, is that there is always that geometric concept going on, right? So calculus, as an example, it has geometry, right? There is something going on, but for a lot of students, it's a lot harder to visualize, right? Because you have just these weird functions that are shaped a specific way, and if you have a lot of experience with math, sure, you can remember what the graph of sine looks like, or what quadratic looks like, or anything like that. But for the average student, they don't have that visual picture, right? So when we say, okay, yeah, we talked about these derivative things, and now you can use it to get the geometry of a graph, students are like, what? I don't see it, though. That's my experience with calculus. Like, we have to really go out of our way to be like, no, here's the visualization. With linear algebra, it's just right there, right? Like, it's always there. We're starting with the study of vectors, which inherently have geometry. So just in the explanation of here's what addition is, we can be like, by the way, here's the geometry of it, right? It represents this sort of parallelogram or triangle-like shape, right? So I just think that's interesting that you just always have the geometry. Again, I just think they're neat. A dated reference? Am I old now? Like, can I reference The Simpsons? Okay, good. I mean, that show is like, it's older than me. No, well, no, I think it's the same age as me. I think it was 1988. Okay, so this is one of the operations we can do on vectors. Now, when we talk about numbers, we think about the things we can do on them. We can do addition, we can do subtraction. We'll talk about that in a minute. But the next thing we can do is multiplication. For a complicated amount of theoretical reasons, there isn't a meaningful way to define multiplication for vectors that has any meaningful geometry or produces any meaningful result. Because you could say, well, naively, well, why don't we just multiply the components? It turns out that has a lot of bad properties and doesn't really work how you would want it to. So we get some stuff that's like kind of like multiplication for vectors that has a lot of geometric meaning, and that's what we care about. And we can talk about multiplying matrices, which is something we're going to start talking about next week. And vectors are special cases of matrices, and if we use that knowledge, we'll understand why we can't define multiplication of vectors. But point is, we can't really multiply vectors. And so without fail, I'll say, like, no matter how hard I hammer that down, students multiply vectors all the time. You cannot do it. We have something called the dot product, which we're going to talk about next week, that is like multiplication, but not quite. But I'm going to say no multiplication for vectors in the traditional sense. But that comes with a nice upside. That means there's no division. So I don't have to worry about division. Yay! But like I said, there's things we can do that are sort of like that. So we're going to start with a definition first. So when we say a scalar, we mean just a real number. And you might say, okay, Travis, why don't we just call that a constant? Because constant has a very specific meaning, right? It means in an equation or formula, it's something that remains static. It does not change, right? That's not really what this means. You'll see why we call it scalar when we talk about what we use it for. There is a specific reason. Scale, right? There's scaling involved. But that's why we chose a specific name for it, right? Because it doesn't, a constant means something very specific. So, but it's a similar kind of concept. So that's why we chose the letter C. So if C is some scalar, then the scalar multiple of a vector u, which is the standard thing, u1 comma u2, right? Just two components, is, so the notation we use, and this is what I'm saying, it's like multiplication, but not quite. We're multiplying a number by a vector. So all we do is we just move this number in. So u1, u2 is going to become c times u1, c times u2. We just bring that number inside. So the reason why we call this scalar or scalar multiplication is because this has the effect of essentially scaling the vector, right? It'll either make it bigger or smaller, and it could change the direction. So if c is bigger than 0, u and c times u have the same direction. Similarly, if it's less than 0, u and c times u have opposite directions. And lastly, cu is, this is going to sound like a funny way of wording it, is the absolute value of c times the length. So remember, this symbol here means drop the minus sign, right? If there is one. So the absolute value of -2 is 2. The absolute value of 5 is 5, right? If there's a minus sign, drop it. Otherwise, leave it the same. Times the length of u. So what this is saying is if this is 2, then 2 times u is 2 times the length. If it's 1/2, it's 1/2 times the length. So it's half as long, right? So that's why it's called scalar. It scales our vectors. So quick example. So let's say u be the following. And c1 is 2, c2 is 1/2, and c3 is -3. So we've got some vectors here. And we've got our first one. Move right 1 up 2. That's u. All right, let's draw c1 times u. Well, what's that? It's 2 times u, which is 1 comma 2. So we just move that 2 inside, right? The numbers become twice as big. So 2 times 1, 2 times 2, 2 comma 4. So we move right 2 and up 4 now. Right 2, up 4. Like that. Similarly, c2 times u it's just 1/2 times this. So we just bring the 1/2 in. So we're going to move right 1/2. So that's in the middle here. And then we're going to move up 1. Like that. Right? And lastly, C3. So it's -3 times this. We bring the -3 in. -3 minus 6. That means we move left 3, down 6. 1, 2, 3, 4, 5, 6. Like that. Okay, again, so I'm drawing all of these vectors from the same starting position. You do not have to, right? So you could have instead done, like, okay, I'm going to draw this one like this. So it moves right 1/2 and up 1. And then you can say, I'm going to draw this one over here. So it moves right 2 and up that amount. And then you can be like, okay, but I'm going to draw this one over here. Like that. Right? You can shift them around. It's fine to draw them from wherever you like. But this lets us have a definition that's related to the scalar multiple, and that's the idea of parallel. And parallel vectors match the intuition for parallel, like the what you think of, parallel train tracks, right? Train tracks are parallel; they run in a line together, right? So we're going to sort of use the same idea, but parallel doesn't necessarily mean side by side. They can be on top of each other too, right? That's totally fine. These vectors I drew all on top of each other are parallel in a technical sense, but that's why I also drew them sort of shifted, right? You would agree that these things are parallel to each other, right? All of them, right? They all run, they have the same sort of, the intuitive idea of parallel is if they ran on for infinity, they would never cross each other, right? That's the intuition for parallel. And this is the same idea. So two vectors u and v are parallel if there is some c so that u is equal to c times v. Right? So you can find some number where you multiply a vector by that number and you get to the other one. Right? So like if we look at this over here, this vector, this green one, if we multiply this vector by, I guess it would be 4, then we get the same thing as the blue one, right? It's easier to see this when they're overlapping, right? If this green one, we multiply it by 4, we're going to get this blue one. If we multiply this black one by -3, we get the red one, right? So they're all parallel to each other. Okay, but geometrically, 4 minus 6, and consider the following vectors. We're going to see if this vector is parallel to the ones I'm about to write down. -2, 3. Let's do 8 pi minus 12 pi. That's our second vector. And our third vector is 2, 1, which we'll call v3. So the question, are any of these parallel to this vector, is asking ourselves, is there some number that we can multiply either of them by to get to the other one, right? So basically, we've got u equals blank times v1. What goes in the blank to make this true? Is there one? Is there a number that works? Yeah, -2, right? So we can stare at this enough and we'll find it. So -2 would work, right? Because -2 times -2 is 4. -2 times 3 is -6, right? That gives us the other vector. Same thing here. So the point here is 2 pi will work. Now, that's not a, okay, we say that's not a pleasant looking number because we're just used to dealing with like whole numbers, but this is a perfectly fine number, right? In fact, it crops up everywhere because, again, the circumference of a circle of radius 1 is 2 pi. So, it's not that weird that it comes up. But the point is, this can be any number. It doesn't have to be a nice whole number. It can be anything. What about this one, though? Well, so we're wondering if it's possible for this to be true. So let's unpack this, right? U is 4 minus 6. This is C times 2, 1. So we can move that C in to get 2C and C. Now, that means we have two equations from this, just like we did earlier. So we have that 4 has to equal 2 times C, and we have that -6 has to equal C. So, okay, there's two ways to sort of approach this. So that first equation, if we divide by 2, tells us that C is 2, right? But the second equation tells us C is -6. Well, that's not possible, right? Contradiction. So that's impossible. So what that means is we can't find this C, right? There's nothing that's going to work, right? Because as soon as we pick one number, we immediately find that we can't get to the other one, right? No matter what we do. So there is no C. So U and V3 are not parallel. So again, this is, you could probably do this by just looking at it, right? You're like, okay, well, if these are to be parallel, I need to multiply this by 2 to get to 4. But then when I multiply 1 by 2, I don't get -6, so that doesn't work, right? So just by looking at it, we see that that's not going to work. But I'm just trying to get us warmed up to these kinds of ideas, right? The thinking of vectors in terms of equations and how we can simplify them and how we can do algebra with them. Because that sort of ends up being the building block for linear algebra. Okay, so we now have addition and we have the concept of scalar multiplication. So what we can now do is actually get subtraction. Oh wow, I'm running out of time. So subtraction. Good news. We get it basically for free. So we define subtraction as a combination of addition and scalar multiplication. And this is going to seem weird initially, but there's a reason why it's useful. Plus -1 times V. So it's like, why would we do that, right? Well, it turns out actually for numbers, we actually mathematically do the same thing. We define multiplication, we define addition, and then that lets us get subtraction for free. But there's geometry still for scalar multiplication and for addition. So this means we also get geometry for subtraction for free. So we can draw this with parallelogram. So let's say we have our vector u, and then over here we've got our vector v. So what we're going to do is we're going to say, well, this definition here is telling us find -1 times v, so we're just going to swap the direction of it. That's all that's going to do. That's minus v. But now we're going to add these two things, right? We're going to add this vector with this vector, and we just complete the parallelogram. Like that. And then right here, that's our subtraction, right? U minus v, or u plus negative v, right? But again, we got the geometry for free. And if you do an exam, I think I have you do this on the quiz. If you do the same thing we did, where you do the drawing first, and then on the side you also do the algebra, you get the same thing either way, right? You get the same move right some amount and then up another amount. So we essentially get this for free. Okay, so I'm actually doing okay. Now that I think about it. So really quick, we've talked about a lot of things we can do in R2. So let's take a detour to R3. So vectors in R3. So what is R3? It's three-dimensional space, right? Ordered triples rather than ordered pairs. So it's a little harder to draw because we have this, and I think this should be, I don't know, don't check my right-hand rule notation here. This might be wrong. It might be, this might need to be X and that might need to be Y. But anyway, this type of thing, right? The X, Y, Z coordinate system. So a vector in R3, well, it's the same kind of thing. Except now we have 3 components, right? This represents X displacement. This represents Y displacement. And this represents Z displacement. So that first number tells us, like if I'm standing like this, that first number is how much do I go left and right. Second number is how much do I move forward or back. And the third number is how much do I move up or down, right? Same exact idea though. So drawing a vector in R3 is a lot harder. You would do something like this, and you might need some kind of arrow to indicate, yes, it's moved up. But, you know, it's hard to visualize. Well, it's not so hard to visualize it. It's just hard to draw. And it turns out everything works the same for R3. So what I mean by that is, how does addition work? You got 2 vectors, you add them up component-wise, right? First 2, smash them together. Second 2, and then third. Subtraction, same thing. Scalar multiplication, you multiply all of them by a number, right? Everything works the same. This geometry, still the same, right? If you want to add 2 vectors, I would not recommend drawing the picture for it, but the same idea still happens, right? You still form sort of a parallelogram-like shape out of the vectors. So everything's the same. So that means if everything is exactly the same and we don't even have to write down the definitions again, that means 3 is not special either. So this is what I'm going to leave us on, is vectors in Rn. So a vector in Rn, same idea, except now you start to see the linear algebra notation. So it's V1, 2, 3, up to Vn, right? There's n of them. We could also write it as a row if we wanted. So V1, V2, V3, dot, 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 Vn. So the point is there's n components. But everything's still the same. How do we add these things? Same thing. Take each component and smash them together. Add them up, right? How do we scale or multiply? Just multiply every number by that number, right? Everything kind of works the same. We start to lose the geometry a bit. Well, let me be clear. We do not lose the geometry. We lose the ability to visualize that geometry. Because what does something look like in 4 dimensions? You can't imagine it. So what we do to visualize those sorts of things is we project it onto R3. Like we take imagine you were a 2-dimensional being. You could not see 3 dimensions, but you wanted to imagine what a cube looked like. What you're going to do is you're going to just look at the cube from different angles on what it looks like on a board, right? So looking at a cube from the front, it looks like a square. Looking at a cube from a corner, it looks like a weird sort of like shape like that, right? You kind of see the various pieces around the corner. So we do the same thing for 4 dimensions, right? A 4-dimensional cube is called a tesseract, which because of the Marvel Cinematic Universe is extremely hard to look up now because you're just going to get results for that, but that's what the shape is called. They stole it from that. So you can actually go to Wikipedia and look up tesseract and you'll actually see like a rotating projection into 3 dimensions, and it looks really cool. You see it from all the different angles that we would look at it, and that's how we imagine what 4 dimensions looks like, is we just think of it in terms of a 3-dimensional object from all the different angles. But the point is, that geometry is still there, we just can't imagine it as easily. But everything else works the same. Everything works the same. So just before we go, I just want to unpack this notation. So an example of some vectors. 1 minus 2 square root of 2, 5. This thing is a vector in R4. So this is a 4-dimensional thing. I could also do 1, 2, 5 minus 1, 6, 7. This is 1, 2, 3, 4, 5, 6. It's a vector in R6. Right, so that number just indicates the number of components we have, and things just work how we would expect. So we're going to basically turn our attention now to, we no longer care about the dimension, right? We can work in any dimension we want. If we want to talk about the geometry, we'll focus on 2 and 3. But anything we define, unless indicated otherwise, works for any number of components. So that's how we're going to focus, and then the examples will use any number of components I feel like, right? Because they're all the same. It doesn't matter, right? Nothing fancy. We'll still generally stick to 2 and 3 just because it's less writing, and I'm lazy. Yeah, we're gonna focus on some of the abstract concepts that we'll need for matrix algebra and stuff like that from this. So with that, I think I am, yeah, it's exactly 7:20. So I will free you of math for the week. And like I said, there's no quiz or anything because the only thing I could construct from this at the very last minute, like last 10 minutes, we talked about R3 and Rn. So I would be like, okay, go draw some vectors. And he'd be like, great, Travis, thanks. And you would finish it pretty quick and he'd be like, that's it. You made me do this before the weekend. Thanks. So rather than having you do something for marks that seems very small, I'm just going to shift it to basically next week. So there'll be like one question about like drawing some vectors on next week's quiz. And then it'll be what we're talking about next week will be on it. So just figured I would spare you a quiz, basically. You don't have to worry about one this weekend. And hey, that means no homework this weekend for me, but probably from your other classes. So, you know, you can't escape homework.
And assignment.